like to interact, and if you don't interact, I still would like to see your faces. Therefore, as way of a stimulus, I decided to propose the following arrangement. This classroom is full enough, but should the classroom, because of a plague or whatever, be not full enough, then I will not upload the lecture on YouTube. Okay? Got it?
Yes.
Life sucks, doesn't it?
Can you these buildings still upload it? For the people who are here?
Or just email. No.
Because
Yeah, I know. Life sucks.
yeah. And if we all kill them, we're still uploading.
Yeah, because then the people that count are 100%. Now. Did you start with the recording? Oh, we read it. Then warn me next time. Okay. And there we are. Good. Now, what we're gonna do today? Oh wait, are all laptops closed? Oh, that's touchy. Okay, what we're gonna do today is discuss type systems. Now specifically, we're gonna talk about the issues that we have encountered with language like Python. We're going to discuss possible solutions to these issues, and then we'll discuss a structured, strong solution to these issues, which is static typing, as present in languages like Java and C#. Now, the issues with Python can roughly be summarized as a bunch of lacks. Lack of constraints. So, how can we say, okay, this function can only accept an integer as input? How can we do that in Python? We can't. We have a lack of structure. So how can we specify that a given variable that's an instance of a class will certainly support some methods? And in general, these two things, lack of constraints, lack of structure, can be summarized as lack of assurances. So we would like to have some basic guarantee that we get some automated system that goes through the Python program and says, you know what, this really does not make sense. So a basic layer of common sense that prevents really stupid programs from running. Okay? Did you ever have the feeling during the project that you write a piece of code and it has a mistake and it doesn't do what you want? And then you have to debug for a few hours or days or whatever, and then you see the problem and you say, what the fuck, this was stupid. Did you ever get this feeling? I mean, come on, why did Python even run this thing? Now, as an example, what is wrong with this? Now only look at the function, def f of x return x times 2. By looking at the function only, by looking at lines 1 and 2, what is x? It says an integer. What do you say? It's an integer. What do you say? It's an integer, right? And yet, look at line 3. What do we give? Do we give an integer? Do we give a string? What is this going to do? Sorry? Nonsense, no. Oh, but you can see from that one. So you get nonsense. So, by looking at the code, it seems that the intention of the user was to get a parameter which was an integer. But actually, we can also give a string. Is that a good example? Are you ever going to find in a single file these in lines 1, 2, and 3? This is going to be in a file, and where is this going to be? Where is it going to be? Right beneath it?
Probably some value.
Probably somewhere else. It's going to be in another file that someone else is working with. So as the program breaks, the mismatch between the definition of the function and the expectation that goes with it, and the wrong usage of the function will be in different places. So now this is obviously very clear because it's put artificially close. But when it's line 3, it's going to be somewhere else. It's going to be line 3000. It's going to be another file. That someone changed midnight in a feverish, panicky attempt to fix a bug, and he introduces another. Okay? Now, so this is clearly an issue. What's wrong with this, on the other hand?
It thinks it's a string, so you always print something.
Are you sure? So x, in this case, is a string. And is a string greater than 100? Are you sure? Are you really sure?
Well, now
Would you bet your testicles on it? No. No, you wouldn't. So you are not sure. Now you are quite sure that 5 plus 5 is 10, but you are not really sure that a string is greater than 100, or not. Right? Or would you bet the testicles of a person that's dear to you? That's another question. Yeah. Okay. So the mismatch here is that what should x be for this to make sense? It should be an integer. But it isn't. And that's a problem. Now, what's wrong with this on the other hand? What do you expect? Oh yeah, really good. Wait a second. Well, what do you expect car to be? If you only look at lines 1 and 2. Yes?
I don't think -1 has a drive function.
Ah, -1 probably. I mean, can you drive number -1 to work? It's kind of weird. Point is, if you look at the code of the function, then what do you expect car to be? An instance of what? Sorry? An instance of a class. Which class do you guess it might be? Car. So we expect the car variable to be an instance of a class like car or automobile or motorized vehicle, right? Something like that. But then at line 3 we keep a number, and the number is clearly not something that has a drive method. Now, even more subtle. This function, would it work if we gave a bus instead of a car? Yes. And is that something we wish here? Maybe. Do you like maybe? No, you don't. Paranoia is what saves you. Why would a bus not be a good idea? Look at the name of the variable. What does that say about what the programmer that wrote function g expected? Did he expect it to be anything that was drivable? No, he said it's a car. If you put a train there, I don't know, maybe it's not a good idea either. So you get this. So we have a name there that says, okay, I expect this to be a car. And that's it. Then you can put whatever you want in it. And in some cases, it will even succeed. Like if you put a bus or a train or, I don't know, maybe a rocket has a drive method, but you really don't want it. Possible solutions. Well, you might say, okay, testing the program should be enough, right? You test it. Is that enough? So I see some... Sorry? Why not?
Because nothing's ever easy in programming.
Nothing's ever easy. Yes, that is a good attitude. Yes, you are getting ahead. So, it is not enough. Why not? Let's say you test the program. How many times could you test? Think about the project 2, okay? How many times can you test it per minute? The whole day. Yes? Not even one, okay? So let's say that you reserve every day, being a reasonably paranoid programmer, a couple of hours for testing. How many runs of the full game can you do in a couple of hours?
As many as necessary.
I guess not. You will be able to do, let's say 20, 50. 50 seems quite a lot, right? You run the game 50 times. Okay. Well, the problem is that the number of possible execution paths within your game are billions, if not infinite. But every time you test, how many execution paths do you take? Just one, literally. So if you know what execution paths are, think about dev 1. Remember dev 1? We're gonna put the slides for fun, you know. So if you have an if, how many execution paths do you have?
4, 2.
True. If you have an if followed by an if, how many execution paths do you have?
4.
No? 4. 4. Why? Because the first if could be, let's say, then or else. Then for the then of the first if, you could have the then or the else of the second if. But for the else of the first if, you could have the then or the else of the second if. Okay? Now, if you have a while loop within an if, so you have while and then an if. And the while loop takes 100 steps. How many execution paths do we have? Sorry? Sorry? A while loop that takes 100 steps with an if inside. You should have that in your game. You wish. Every execution of the while loop runs the if, so that's 2 options. The second execution for every one of those options adds 2 options, so we have 4 now. The third execution for every one of the 4 options adds 2, so that's 8 now. It is 2 to the power of 100. Is that a small or a big number, I wonder? What do you think? Yay big? Yay big? Yay big? It's a huge number. You know, it's those numbers that people say, yeah, the number of grains of sand in the beaches of Miami, whatever. Okay? So these are all the possible things that can happen for every possible execution of your program, and they must all potentially be tested. So, and you can test 50 of those. That sounds kind of like not enough. Now, of course, if you test, what you can see is that there is a bug. Right? You test it, the game breaks, there was a bug. You test it, the game works. Does that say that there are not going to be bugs later? Obviously not. I mean, is that your experience? Have you experienced that you test the game, and yesterday it ran just fine. But today you press this button, and now it breaks. Yes or no? Have you seen this with your eyes? Has this done pain to your heart? Why did it break? We didn't change the code and now it's broken. So, take a look at this piece of test just for an example. Now this is the G function that we saw before that only works when you put a car in it. Okay? And assume that Mercedes SL500 is actually a car. It's an instance of a car. Okay? So whenever you call line 4, this thing is going to succeed. When you call line 2, it's going to fail. Now tell me, how many times do you think we would need to run to test this piece of code to be sure that there is no error? Sorry, I heard something. Why at least 100,000? What's the probability that the condition of the if will be true? That it's going to be true is actually very low. The probability that the condition of the if, now the if takes a random number between 0 and 100,000. And then we compare this random number between 0 and 100,000 by 99,999. 99,999. So this means that most times this condition will be false. Now 99,999 times this will be smaller. Now the last case, in the last case it's going to break. So how many times would we need to test this? Well, if you run it once, this is going to be false. You really can bet your testicles on this if you run it just once. You run it twice, you can bet your testicles again that it's going to be false. You have to run it a lot of times. You have to run it at least 100,000 times. But even then, you have no certainty. So why do you think I put this weird condition? Because that condition means if you think about a game, that your game breaks if someone presses this button and then that button, and then drags something in some direction. So these weird combinations of behavior that cause bugs in programs. So that is something that happens very rarely. Now in this case it's actually just probabilities, but in that case, as you test the program, you're not going to test all possible sequences of clicking buttons and selecting units and making moves. So there is one random probability somewhere lurking and trying to break your code that's not going to happen as you test. Okay, this is quite bleak. So testing is not enough. So what we want is we want our programming languages to perform these checks for us. And clearly nonsensical programs that really make no sense should be rejected by the compiler itself before we even get a chance to run the program. So we want to have to define a basic set of basic requirements that guarantee that if these requirements are respected, the program does not contain some very stupid bugs. So what we really would like to get is a programming language that tells us, you know, this really makes no sense. So a language that says, you know, line 2 as making sense. Because the function G wants a car and you put a number, right? The computer should be able to determine that at the very least. So, enter static typing. Static typing is a process such that the language verifies, by means of the compiler and a bunch of rules that we're going to see shortly, that all variables are correctly used. And correctly used here means something quite simple. That all operations, all methods we call on a variable make sense, are supported by the variable. So if you have a variable that contains an integer, what kind of operations will you be able to do on it? Take an example. 1 is an integer, so what could you do with it? You can increase it. You can multiply it by 10. But you cannot call the drive method on it. Okay? If you have a car, you can call the drive method on it, but what can you not do on a car? What do you not want to be allowed to do if you get a car variable?
Do mathematical operations.
Multiply it by 2. Okay? Good. Now, or actually, if you just do that, would be awesome, but yeah. Now, so when declaring a variable, this is the basics of it. When declaring a variable, a function, or an argument in a function, what we will have to do, and we've already seen this in action, is we'll have to specify what type the variable, the argument, or the function is. And this type is, in some sense, what kind of data, what sort of data is allowed to use in the variables, and also determines what kind of operations may be performed on it. Types can be primitives. So we can say a variable is a primitive type, like an integer, a string, a boolean, a float, whatever. Types can also be custom, like classes. We can say, okay, this variable is of type my class. Car, bus, relationship, man, woman, dog, whatever. Or it can be composition. So we could say, okay, we have a list of cars, we have a function that goes from car to integer, whatever. Now, especially in mainstream languages, the specification of the type of variable will be done explicitly by hand. So you have a variable like x, and you say int x to say, okay, x is an integer. This leads to a common idea, which is wrong, that if you want to have static typing, you must write more. This is true for Java and C#, very true. So you will notice that Java and C# are much more verbose than Python. But it is not true in general. You have languages with static typing, like F#, Scala, or Haskell, that have static typing, but that do not require type annotations. This is just to prevent that you go on Reddit and complain, yeah, but I do not like static typing because it makes progress more verbose. There is enough stupidity in the world already, I would say. Now, a variable declaration in C# or Java is prefixed by the type of the variable. So int x declares an integer variable. String s declares a string variable. Float f declares a float variable, and so on. Okay? So this here becomes, when we put types in it, int f, int x, return x times 2. So what have we specified here? This is actually code that you could copy in Java or C#. What has changed?
What type of variables
So which variable do we have there?
X.
We have x. And what we said is that x is an integer. So we can't put a string anymore in it. What else do we say about the function, which is quite important?
Function returns an integer.
The function returns an integer, which is also something quite important. So, is it possible to write this as it was possible to write it in Python? Why not? So what you're telling me is that if I write this code into, oh god, 8 emails. Oh, what's wrong with people? I think they hire some people just to send emails to colleagues. They literally just grade their performance after a year, just by how many emails they sent. And if enough emails were useless, then they get a monetary bonus. Okay, anyway.
You just bet your testicles on
No, this is sorry, wrong language. My apologies.
But
Yes. Okay. Oh, look. Sorry. Now, look. This is actually quite random chance, but here is the function, the very same function, almost the very same function that we just saw. Okay, got it? Besides that, it's a static function, but that should not be a problem. Now, if I call this with nonsense, look what happens. Ooh. What do you think? The red worm there, is that a good thing or a bad thing?
It's bad.
Yeah, it's a bad thing. Now, if I'm gonna ask Visual Studio to run the program. So, he starts, he's compiling. Boom! It doesn't even start. Look! And what it's telling me, which you can't read from a distance, or actually you can because we have the screens, but I'm gonna read it. It says oh, wait a second. The first very important bit is line 14. Why does it say line 14? Because the error is on line 14. Okay? Then it says argument 1. So the error is not only on line 14, but it's about the first argument of the function. Yeah, you might think that's obvious. But it isn't. And then it says cannot convert from string to int. What does that mean? If you want, we can turn it around. I was expecting an int, but I got a string, and I can't convert the string to an int, so I can't make an int of the string. It's not obvious how to do it. Yes? No? Ready? Yes? Good. So, the program is refusing to run. Now, funnily enough, we could add an argument like this. What's the error going to change into? Argument 2. Can we convert a string to int? Okay? And that's basically it. So, suppose on the other hand we write something like this. We translate this code into, well, first of all, x is now declared as an int. That's nice, because we say I really want to read an input of an integer. But then what do we have to do with console.readLine? What does it return? What do you think console.readLine returns? A string, which contains whatever was typed by the user. Is that always going to be an integer? No. But then what do? We parse it. int32.parse. What do you think it does? It converts the string into an integer, or throws an error if the conversion cannot be done. Then, if the conversion has succeeded, we can actually assign to x, to variable x, the value that was written as a string on the console. Then we can do the comparison. Does the comparison make sense now? Because x is now an integer, so an integer could be smaller, could be equal, could be greater than 100. Now, once again, we translate this. Look what's happened. What more information do we have?
Car comes from a class car.
The car variable is an instance of the car class. So can I put a bus in there?
Well,
Can I call the G function with an instance of a bus?
no.
No. So I'm clearly saying that G doesn't want something with just the drive method, which the bus would also be. So the function G doesn't take a drivable, something that you can drive as an input. It takes literally a car. So what happens? Why is line 4 not accepted anymore by the language?
Car can't go
No.
It's outside the menu.
Almost. What's the problem of line 4?
There's no type.
Sorry?
There's no type.
Yes. What is not an object?
The
-1 is not an object, and very specifically, -1 is not a car. So -1 is not a car, and as such, it can't be given to G. The G function expects a car. Is -1 a car? No, it isn't. You have to create an instance of a car to be able to call it. So, just for your information, what this could look like is, okay, suppose we had here this very same implementation.
There's a car named Cactus. There will also be a car named Science.
Nope. Unfortunately not. Because the -1 is always a number. Okay. So, here, the class car, then public int drive, which returns, I don't know, 100. Okay? Now, I could give to G a new car. And this is going to work. And if I actually also print the result, what am I going to see? As a result, this is a working program. If I run it, this is going to work. What's it going to print? 100. And why is line 14 acceptable? Why is G called correctly here? Because I'm giving a car to it. Now, I could say my pretty car here. And I could say car, my pretty car. It's the same, if you want to have a variable. Now, what is my pretty car? What's the type of my pretty car?
car.
Sorry? What's the type of my pretty car? What do you think it is? Car.
That's also a car.
That's a car. What is my, the question is, what is my pretty car? Is that a string? Is that an integer? Is that a float? Is that a car? Yes, it's a car. And now the language accepts it. And what we get is 100. Good, 100. Now, should I try to put -1 here? Then, no, it doesn't bode well. What's the error going to say? It's going to say -1 is not a car. Actually, what it really says is, okay, first of all, line 15. So it says, argument 1 cannot convert from int to car. Because we gave an integer, but the language has no idea how it can change an integer into a car. And he's right. Okay. So, now, to go back to a bit of mathematics that you all love and appreciate. So this adds a new layer of theory besides the stack and heap. So we will do less stack and heap now. But I don't know if you should be happy about it or not. I would go with not for sake or for keeping sure. Now, how do we describe clearly and precisely all these relationships? So how does the compiler come to the conclusion that it has to tell us about a type error, or that it can safely run our program? Now, first of all, let me ask you a question. If I run the compiler twice with the same program, is it always going to give the same result, or is it going to change based on the mood of the compiler? Does anyone expect that if you run the same compilation on the same set of sources without changing them on a sunny day or on a rainy day, that on a sunny day the compiler will give less errors because he's happier? I'm assuming, of course, not. So this means that the compiler is actually just a machine that is defined, and its work is defined based on very precise rules. And by the precision of these rules, what we get is reliability. That is always the same result. Got it? Yes?
Does the compiler
Have a mood? No, it doesn't. Nor a heart. It's a cold thing.
Yeah.
Yes.
But does it run the whole program always?
Almost.
All the paths?
Yes, almost. So, what it does, it runs a bunch of typing rules that look like the rules for the stack and the heap, but are simpler. It runs through every line of code. It tries to apply these rules for every line of code to see if they break any of the requirements of the language. If they do, then the language is trying to do something that is not allowed. And so we get an error. So it runs a sort, So first of all, I'm going to show you what typing rules are. Then, so an example of how they are written in general. Then I'm going to show you most of the actual typing rules. Now typing rules typically look like this. Now that's not a fraction, like 10 over 5. It's not. So what that means is, if A and B are true, then C is also true. Okay? Is this verifying or very complex? So what's above are the preconditions. What's underneath is the result. Okay? Good. Now, as a concrete example related to programming languages, suppose, how do you read this? If I
want to buy a new car and I have
yes, that's a lot.
120,000, then I buy a Mercedes SL 500.
Okay? Got it? I would buy an SLK 350 today, with respect to when I made the slides. But besides that, yeah. No, neither. I would buy used. They lose value like crazy after 5 years. Anyway, another example, slightly more related to our experience here in the Netherlands. How do we read this? How do you read this thing here?
False, false, false.
No. You have to read the rule, not slide. Almost. If it is raining and I have my umbrella with me, then I open my umbrella. So this is literally a mathematical notation for an if then else. Now, why does this make sense? Why do you need both conditions? Do you open your umbrella if it's not raining? No, unless you're 5 years old and you want to show your new Elsa and Anna umbrella to your friends. And if it's raining but you don't have an umbrella, can you open your umbrella? No, you cannot. Okay? That's kind of the idea. Now, why do you think something like this will be relevant to type checking, to verifying the types of the program? What kind of conditions do you expect we're going to find? And you're using it as an integer, then you're fine. Yes, exactly. Things like, if it's an integer and you're using it like an integer, then you're fine. Something like this. That's why we need all these checks, like if it is so and you're using it right, then good. Now, let us apply this machinery to programming languages. What we will do is we give a weak, admittedly, specification of a modern compiler, which looks exactly like a coarse, a raw execution of the program. So it's like running the program, but not with actual values, but rather just with the types of things. What we're going to do is we're going to specify all of these. Yeah, this can be a source of hilarity. Yes. So what we're gonna do is, instead of the stack and the heap, we're gonna track the declarations of variables. Since declarations is quite a long word to repeat in 6 points on a slide, then the slide becomes longer, we're gonna call it the D. Okay? Now, every typing rule will be able to check the D for type declarations, add or remove things to the D, so make the D bigger or smaller. I'm gonna try to stop now.
If I will use my D, your stack will be not empty.
Now, and the point is what we're gonna find in the declarations is that every variable, now in the stack and a heap, every variable was coupled with what? A reference or its value. So what you found on the stack and a heap was the value of every variable, right? Is that what you remember? So in the stack and heap you put the value of all variables. But here what we're gonna put in the declarations is the type of every variable. So let's begin with the simplest typing rule. What we find on the bottom left side are two things. A piece of code, comma, the current declarations. The declarations of all variables found so far. What we get back are two things. The type of this piece of code and the new declarations that result from running this piece of code. What we find above are possible preconditions that need to be met before we can say this. Now, T space V semicolon. What is that? What does that look like? Almost.
Like variable.
Yes. What is T gonna be? What do you think T is gonna be? Not an integer. What if I tell you T space V semicolon is a type is a variable declaration? So in declaring a new variable, what do you think then that T might be? A type, like int, not an integer. An integer is a value, like 5, but the type integer, so int. Or T could be, make another example. String, not a string, just string, so any string. Another example of what T could be. Float, bool.
Class.
Not class, but car. Yes, car. Got it? So any declaration will work the same way. And what do you think V is? No. The name of the variable. Is it always going to be V? No. No. But as a generic variable name, I picked V. Actually stands for variable. Okay. Now, so look what happens. Did someone say something? No. Now, we declare variable V with type T. So what we do is that we return. Do you remember how we read this? Oh, come on. Really? Please. Don't you remember how we read something like this? What? Oh no, void is, so this thing, this declaration here, has no type. And no type, we say void. But what I'm more interested in is that what happens to the declarations of variables when we declare a new variable. Yes?
If like a string becomes an integer, the value first thing is the
V. What?
T
Is a value.
T first. T is string, the value, the variable would be an integer.
No. This is a declaration, so it's like int x.
Yeah, I know, but then in the second you use the same V to get to the utility. Also V.
Yes. Guys, oh no, it's the same V. It is the same, just in cursive. what this means, come on, does no one have any idea what that could be? We declare a variable, so what do we do with the declarations? Yes? Variable v gets type t, so we put in the declarations, so that reads d, where v goes to t, is connected to t. Now, to visualize this, what was t and what was v with respect to this example? T was int and v was x. Agreed? Now, this is the beginning of the program. This is actually the whole program. So in the declarations we have nothing. The program counter is not actually a declaration, but it's just to know where we have gone. What do you think is going to happen as I press next? I'm going to have to add something to the declarations. What? X, okay. What's the value that we're going to... Okay, so what's the value that's going to be connected to X? Yes? Int. Why int? Well, look what it's saying here. It says the variable will be connected with its type. So what happens here is that I'm going to see X has type int. Does that make sense or not? Is that still recording?
Yeah.
Okay. Good. Now, suppose we assign an expression to a variable. Now, so for example, we say x is equal to e. X is whatever variable we might think of. So it's not literally just called x, it can be called whatever we want. And e is whatever expression. Make an example of an expression that we could assign to a variable. Yes, you do have an idea. Come on, an expression that you can assign to a variable. Let's say the variable is called v. V is equal to, and it's an int.
6.
V is equal to 6. Well done. No panicking. Come on. I'm not gonna kill you. Yet. Another example of an expression. V is equal to 10. Come on, make it more complex now. 10 times 2. Thank you very much. Does a courageous person want to make an example where you assign to a variable an expression that has to do with a new instance of class? Like car is equal to?
Mercedes.
But I want a new one. New car with then brackets and parameters. Okay? So that's the expression. That's any possible thing. Now, assignment within a bunch of declarations. What I can tell you right away is that assignment, has no type. Assignment is void. It's just something you do, but it doesn't return anything. And, oh, look, what does this mean? Does assignment change the declarations? Does saying that a variable x is now equal to 10 and it was 5 before, does that change declarations?
No.
No. And is that wish? Is that what we want? This is what you want. You change the value of a variable, but it doesn't change type.
Yes.
Clearly, yes. Good. But suppose that x was an integer. What do we require of the expression e that we assign to our variable? Sorry? The expression has to be an integer. So we can't say that with a variable x, which was an integer, what can we not assign it? Make an example of something that you can't assign it. A string, like? So if you have x, it's an integer, you can't say x is equal to?
Hello.
Hello, yes. You can't say x is equal to hello. You can't say x is equal to new car. So what we need to do is, okay, we run type checking on expression e. And what we expect is that the expression will not change the declarations. And what is t? What do you think t is? And it gives us t back. What is t? the type of? No, not of the variable. It's the type of the expression. So if you do x is equal to 3, first you type check 3. What is the type of 3? It's an int, right? Is the type of 3 int? Is it string? Is it bool? It's int, yes. Okay, then the type of the expression is t. Can be whatever. What does t need to be with respect to the variable? Yes?
Int.
It needs to be int. But where do we know the type of each variable? Where is it stored? Where did we say we were going to put the types of all variables? Sorry? Not in the heap. In the declarations, which are now a substitute for the stack and the heap to an extent. So what do you think this means, d of x? The declaration of x, that is its type. So, suppose here on line 1, we have int x and then x is equal to 5. What's going to happen as I press next? What's going to appear in the declarations? Yes, x. X has int as a value. That's it. Those are the declarations. We're not tracking the values. We don't care about values at this point. We just care that things have the right type. X is int, which kind of also makes sense if you say out loud, x is int. Is x an integer? Yeah, which one? We don't care at this level. Okay, and next, what do we do? Well, we take a look at the type of 5. What do you think the type of 5 is?
Integer.
It's an integer. Okay, so with respect to this slide, where's int? Where's the int that is the type of 5?
T.
It's t. That's the type of the expression. Okay, and what is d of x going to be? Int. Where do you look? So, these are the declarations, the d, and d of x is this. That's the value connected to the name x. Is d of x equal to t? We just said t is int, d of x is int. They're the same. This program is allowed to continue. It doesn't give a compile time error. Okay? Now, when you find a variable in an expression, like you say x plus 3, then what is the type of the expression made up of just a variable? It's not always going to be int. But where do we look for the type of a variable? In the declarations. If you don't find it in the declarations, then it wasn't declared, and it's a mistake. So, suppose now that we have something like int x is equal to 10, x is equal to x plus 5. As I press next, what's added to the declarations? Hello? What's added to the declaration?
A few minutes.
Do you need to take a break?
Over 4 minutes.
Okay. So, what's going to be added to the declarations? X is integer. Yes. No hard questions. Okay. What have we done with 10? What do you think we've done with 10? To be able to say we go to line 2, line 1 was correct. If 10 also was of the type found in the declarations of x, which in this case is int. Okay? They're both int, so we can go on. Okay, now, to validate line 2, is that going to change the declarations? No, why not? have to,
So,
we just have to check that we use x correctly. We're not going to change the fact that x now suddenly becomes a string. That would be crazy. What we say is x was an int, it stays an int, but we make sure that what we assign to it also is an int. And is it an int? Well, okay, it's the sum of two things. What is this? It's an int, you all agree. And what is x? Where do you look to say that it's an int?
Declarations.
In the declarations. Here. Okay? Good. Now, and so we can go on and say this program type checks. So now you can run it. Another very simple typing rule is the one that types a constant value. So if we find something like 5, do we change the declarations? Does the number 5, the presence of the number 5, change the declarations? Obviously it doesn't. But the number 5 doesn't change declarations, but has type
Int.
int. If you find a floating point number like 3.5f, does that change the declarations? You write 3.5f somewhere, does that declare a variable like my given variable? Obviously it doesn't. But 3.5f has type
Float.
float. Yes. Same goes for strings. The string hello world, it doesn't declare all of a sudden a variable, or even more funny actually, it could undeclare a variable. That would actually be a fun language, that a string undeclares a random variable. But no, that would make no sense whatsoever. So look, and where do I see here that the string s, that any string s does not change the declarations? Where do I see it?
Yeah.
On the right side,
Because on the right side, what do we have?
the new state of the declaration.
And what does that look like?
String.
Sorry?
It looks like a string.
No, that one.
Just
Those declarations are exactly
Like
the same as the input declarations. Got it? For Boolean constants, we have the same, etc. Now I guess we can take a break. Okay, guys, you may put your phones and laptops away. So, in some cases, we will find more complex typing rules that mix together other typing rules for the benefit of typing complex statements. The simplest example is the typing rule for an operator like plus. To be able to say that A plus B within a bunch of declarations D is an integer, well, first of all, we know that the declarations are going to change or not going to change when adding two things together. Not going to change. It makes sense. If you do 5 plus x, that's not going to change the type of any variable in your program. Okay, then, what do we need the type of A to be? An integer. What do we need the type of B to be? Also an integer. And what is the type of A plus B going to be? An integer. Does that make sense? Yes. Now, then we could say the type of A might be a float. The type of B might be a float. Then the type of A plus B is going to be float. Now, here's the question. Why do we need the declarations to determine the type of a sum?
you get the result you expect. You want.
But why? What could A or B, what form could they take that requires the declarations to determine their type? If we need to determine the type of 3 plus 5, do we need the declarations for that?
No, the machine does.
The machine needs that to be sure. But the point is, what kind of sum, what kind of piece of code would require the declarations?
If you want to precise the integer.
No. Yes? Make an example of a sum that requires the declarations.
X plus 5.
X plus 5. So for x plus 5, who's going to be x? Here, A or B? It's going to be A. Who's going to be 5?
B.
B. So to determine the type of x, do we need the declarations? Yes, because just from the name x you can't guess the declarations. So you need to look at the declarations. What was x declared? If it's int, then we're fine. Otherwise not. That's why we need the declarations. Oh, also another case is the case of string. Now if A is a string and B is a string, A plus B is also going to be obviously an int. It's also going to be a string. Now, oh wait a second. Yes. Now we're going to see more of this, but for the moment, for simplification reasons, suppose that A is an int and B is a float. What is A plus B? It's a float. Why is it a float? If one is an int and the other is a float, why is there some a float? Sorry? Yes, but why? Why not an int? Yes?
Float is an extended int.
Because we could say that float is an extension of int. So if you have a number like, if you have a number like 5, can you convert that to a float?
Yeah.
How do you do so? 5.0. A number like 10, can you convert that to a float? Yes, 10.0. If you have a number like 10.5, how do you convert that to int? You can't. 10.5 is not the same as 10. So you can say, okay, I get a close approximation of it, but it's not the same, so you would lose information.
Sir,
Yes?
it depends on the programming language, right?
Yes. But typically the conversion from int to float is safer, much safer than the conversion from float to int.
Yeah.
Much safer. Now think about the fact that 0.01, 0.1, 0.15, 0.2 would all be converted to 0. So numbers that are different as floats are not different when you convert them as ints. That seems like a lot of information that we might be losing. Now, suppose that we have two statements, two lines of code, which I call A and B. And these lines of code, A and B, are executed one after each other. So this is literally line A followed by line B. Okay, so we type check A or B first. Why A?
Because that will come first.
And so the declaration, could the declarations of A be used in B? And the other way around? Could the declarations of B be used in A?
No.
What do you think?
But if A is floated, then you can.
Are you sure? Do you have to declare first, or can you just use stuff and then declare it later? You have to declare first. So, where do you see the fact that declaration comes first? And where is A declared? Where might the declarations that are contained in A end up? So suppose that A declares something. Where are those declarations going to be found? Where? It's a very specific place.
Left side, that's right.
Yes. Look above. Where are the declarations of all variables that might be declared in A? A is a piece of code.
D1.
Yes. Please shout it.
D1.
D1. Why in D1?
Because it says so right there.
Because it says so right there. What this is saying is that, okay, you have the declarations D that contain all variable declarations found so far. Then now it's the turn of instruction A. So we type check A, with the current declarations, because those declarations are valid. And what we get is, we expect nothing specifically for type A to be able to put a semicolon in, and then D1. So D1, will D1 contain everything that was contained in D? What do you think? Yes, plus potentially something more. Then, look, we type check B, but we want declarations. D1. So, everything that we declared in A can be used in B. And then B gives us new declarations, D2. Are the declarations of D2, do they contain everything that was in D? Yes. Do they contain everything that was in D1? Yes. So here's an example. The declarations D are empty. Nothing yet. Then we get D1, that's x int. Then we get D2, that's x int, y int. And then we get D3, that's going to be and y int. They keep growing, the declarations. X int, y int. And we're done. Got it? Good. Now, kind of information of that is good. Okay. Suppose on the other hand that we encounter an if then else. Now, and if then else is if C, then A else B. What is C? I mean, make an example of a piece of code that we could find in place of C. X is greater than 10. Then what could A be? Print bigger. And what could B be? Oh, nice. Print smaller, okay? Could also be something more complex. Typically, it will be. Now, look, what do? We type check C with the current declarations. And what do we get? What do we expect from the type checking of C? That it's a Boolean. Does that make sense? Is the condition of an if then else acceptable if it's not a Boolean? No, it isn't. We want it to be a Boolean. Then we type check the then side of the if then else. Now it's going to give us a type which is usually going to be void, but it could also return something. So assume for the moment that type T is void. Look what A does give us back in terms of declarations. What happens to the declarations after A is type checked? They're changed. Why? When could that happen? Because variables might have been declared in the then block of the if. Is that allowed? Of course it's allowed. Then we type check B. And we get a new declaration, D prime. Why? Because variables might be declared in the else block. But look at the peculiarity. Why do we type check B with the original declarations? If we run the else code, have we also run the then code? If we run the then code, have we also run the else code? So you either run the first or the other. So the declarations made in one of the branches cannot be used in the other. Also notice that the if then else here, it gives us back the original declarations. Why? Can the if then else declare variables? so it can't say either or the other. So safely it says whatever you declared in A or B, we don't know if it happens, so we ignore it. I'm gonna show you the example here. Now suppose we have int x equal to 10, int y equal to 20, so the declarations are x int, y int. These are the declarations at the entrance of the if. Okay? And what do we check? So first thing you check to decide if an if analysis is correct.
The condition is Boolean.
The condition has to be Boolean. Now, the condition is something greater than something else. So that might be Boolean as long as the parameters, the left side and the right side, have to be the same. And in this case, are they?
Yeah.
They're both int. So they can be compared. So we're happy. Good. Then, what are we going to type check first? The then side. So lines 4 and 5. Okay? So we type check lines 4 and 5. We begin with line 4. This means that we took a jump inside the new context. Okay, program counter is 4. What's going to happen next? What do we add to the declarations? Z is string. Okay, then can we do console.writeLine Z? We can. Why? What does console.writeLine expect? And what is Z? And what is Z? It's a string. Console.writeLine expects a string. What we gave it is a string. We're safe. Okay, good. And now? Ooh! Where's Z? Where did Z go? People, stuff disappeared. What happened? No. Do you know anything about the condition? No, you don't. We're not running the program. No, it isn't.
Jumping back to your old declaration.
Sorry?
Jumping back to your old declaration.
I'm going back to the old declaration. So the then block, lines 4 and 5, have been type checked correctly. This was the result. Okay? Now what we have to type check? The else block. And does the else block use the declarations of the then block? No. Because they are independent. Either one or the other ones, but never one after the other. So we go back to the declarations. Now these declarations are exactly the same as the ones we had on line 3. That's when we began type checking the if. So now we jump inside, we add Z as a string, and console.writeLine is successful again. Okay? Now, I want to show you this in code. Oops. So we can throw all of this away. Okay. So, int x is equal to 5.
Yeah.
Int y is equal to 10. If x greater than y, what? If x is greater than y, string s is equal to s, float f is equal to 3.14f. And then console.writeLine s plus f dot plus. Okay? Then in the else, I'm going to say string s is equal to s, and then bool b is equal to false. Now, what are the declarations on line 15?
X is integer.
and y is int. Okay. What are the declarations on line 19? No. I disagree. X is int and y is int. And then S is string and F is float. Does this make sense? Yes. And now, what are the declarations here? X is int, Y is int, and now wait. Guys, last line. What are the declarations on line 27? Huh? Declarations on line 27. Come on. I need 4 of them. Okay, I need a bit more. That's half of the answer. So for that you get 0 points. But you have a chance to make it full. Come on. What's int, what's string, what's float? Yes? X is int? So X is int, then? Y is int, yes? B is bool, yes? And S is string. Okay? What are the declarations now on line 29? X is int, Y is int. Let's say S is string. No. Because these languages do not allow you to. Because it's outside of the if then else. If you go back here, this is the definition. This is just how the language is built. Why do you see, where do you see here that S is string is not going to be included? Which one?
The last on the right down.
The last on the right down here says, and then you go back to the initial declarations. Okay? That's just how it's defined. I mean, it could make sense to say if both the if then else, if both the then side and the else side declare the same variable, then just make it accessible. Okay, that could be done, but we don't do it. Okay. Now, the declaration of the while. Oh yeah, that's a high-tech correction. The declaration of the while looks very similar. So we have while C, and then B is the body of the while. Okay, and then we have lots of declarations. What happens to type check? How do we type check a while loop? What do we type check first? Yes? I heard it. And what does it have to be? A boolean. Does the condition of the while declare variables? The condition. Does it add declarations? I mean, in the condition you can't say int x. You just use stuff, so you don't change the declarations. Then, what do we type check? B, the body. Can the body declare variables? Yes. And where do we see that? Not the D. But, which D is it?
D1.
D1. Which has a different name, that's a 1, that's D1. If it has a different name, it means literally that it could be different. But then the whole while loop, which variables does it use? The initial variables or the new variables after the body declaration? The initial ones. Oh, yeah. So, that's because it's outside the body again, exactly. So if we had something like this, y x greater than 1, x is equal to x plus 1. These are the declarations. So at the level of the y, as we get into the condition, d is equal to x int and y int. Right? Because x and y are declared. Then inside the body, at the end of the body, we have also s and f declared. But when the body ends, we go back to x and y. But I mean, why can't we say, okay, but you could say that on line 23, you have S and F, right? Do you have them?
You can have them.
But-
Only if the condition returns true.
At least once.
Could the condition be false right away? In that case, would you declare the string and float? No. So that is one of the reasons, but actually it's also a question of consistency. Okay? I would say, are you feeling tired?
Yes.
Do you want to go on for a couple more hours? No, we're done. Okay, thank you for the attention, and the rest of the presentation we'll do next week. This is all before you run